Hello, Glendale Community College. This is Dr. Kim, and we're going to continue on with predicting the products. This is the fourth video in the series. So, for Chem 130, there are actually 4 different types of reactions where you have to finish the products. 1 is combustion, 2 is single replacements, and we've worked extensively on those. 3 is acid-base neutralization, and 4th, we do have to predict the products for double replacement as well. This is fairly new, so make sure you remember that you have to predict products for double replacement reactions as well as the other 3. So let's try an example. Here we have K3PO4. Can you name that? You're correct if you said potassium phosphate, and it is soluble according to our solubility rules number 1. Potassium compounds are soluble. We're going to react that with MgSO4. Do you know what that is? You're correct if you said magnesium sulfate. It is also aqueous. If we look at our solubility rules, rule number 5, sulfate is soluble. So these are going to be reacted together, and we have to predict the products. We don't give you anything but a big old blank. So let's think about this. What kind of reaction do we have? Well, is it combustion? Combustion is always a hydrocarbon plus oxygen. So no, we don't have that. What about single replacement? That requires a single metal by itself. No, we don't have a single metal by itself. What about acid-base neutralization? Well, do we have an acid? That's a chemical that has a hydrogen that can pop off. I don't see that. We also need a base. That's a metal with hydroxide. I don't see hydroxide there. So what about double replacement, the new one? Double replacement reactions require 2 metals with 2 nonmetals. Well, here we have the metal potassium with nonmetal phosphate. And we have metal magnesium with nonmetal sulfate. So yeah, this is going to be a double replacement reaction. So in the double replacement reaction, we have a double switch. The 2 metals are going to switch places with each other. So let's look at what our products could be. So the potassium is going to go with the nonmetal that's bonded to magnesium, which is the sulfate. And then the magnesium is going to go with whatever potassium is bonded to, and that is the phosphate. Now, whenever we put a metal and a non-metal together, we have to check the charges. One thing we don't do is bring this 3 over. Do not copycat. K3PO4, we do not bring the 3 over K3SO4. That is wrong. We have to check our charges. What's the charge on potassium? It's in the first column of our periodic table, potassium, and that makes it a +1. What about sulfate, SO4? If we look at our periodic table, SO4 is a polyatomic ion, and it has a 2- charge right there. So that's a -2. Well, that doesn't add up to 0, and compounds have to be neutral. +1 - 2 isn't 0. That's not neutral. What do I need to make this neutral? Do I need another potassium, or do I need another sulfate? You're correct if you said another potassium. We actually need 2 potassiums to go with the sulfate. So that would be K2SO4 is the correct formula. K2SO4, because our charges tell us 2 potassiums for every 1 sulfate, because +2 - 2 is neutral. Let's do the same thing with the Mg and the PO4. What is the charge on Mg? It is in column 2, right there. Mg has a charge in a compound of +2. What about phosphate, PO4? If you're thinking it's polyatomic, you are correct. So PO4 is a polyatomic ion right there. It actually has a charge of -3. Oh boy. We have a 2-3 combination. Does anyone know what to do with a 2-3 combination? Well, you're correct if you said we need to meet at 6, the common denominator. So I'm actually going to need how many mg's to get to plus 6? You're correct if you said 3. Plus 2, plus 4, plus 6. Now my mg's are plus 6 with 3 of them. How many PO4s do I need to get to minus 6? You're correct if you said 2 of them. Minus 3, minus 6. Now I have plus 6 and minus 6. That is neutral. So there are 3 mg's and I have 2 PO4s. So I need to put that in parentheses with a 2. So the correct formula is actually mg3 in parentheses PO4 twice. Always check your charges when you write your products. Every time you put a metal with a non-metal, you must check your charges. Do not bring numbers over. This 3 does not come over. Don't copycat. Copycat is wrong. Now, the next thing we need to do is figure out our states. So we need to look at our solubility rules. We are looking at K2SO4. So we're looking at sulfate or potassium, whichever we find first. Rule number 1, potassium compounds are always soluble. So what does soluble get in parentheses? You're correct if you said an AQ. AQ for aqueous. The other one is MgPO4. So we're looking for Mg or PO4, whichever we come to first. No Mg, no PO4, no Mg. Aha, 8-phosphate, PO4. It's on the insoluble side with no exceptions. That means it is insoluble. So what does it get? You're correct if you said an S. So did anything actually happen in this reaction? Did we do anything? Well, we started out with 2 aqueous compounds, meaning dissolved and floating around as separated ions. And then on the product side, the Mg and the PO4s, when they floated around and banged into each other, they actually stuck, bonded, sunk to the bottom as a solid. We call that precipitation. So this double replacement reaction is a precipitation reaction as well. So finally, we do need to balance. I'm going to let you pause and balance this reaction for me, please. Go ahead and balance it. Okay, we're back. So I hope you were able to balance this reaction. Notice we have 3 mg's here, so let's put a 3 in front. That balances our mg's. That gives us 3 SO4s. So we need to put a 3 in front. That gives us 3 SO4s on both sides. Now that gives us 3 times 2 is 6 Ks. We already have 3 Ks, so a 2 in front will give us 6 Ks. That gives us 2 PO4s, which, wow, we have on the other side. Let's double check. 6 Ks, 6 Ks, 2 PO4s, 2 PO4s, 3 mg's, 3 mg's, 3 SO4s, 3 SO4s. So I believe this reaction is balanced. The 1 is optional. Very good. I hope you were able to follow along that double replacement reaction. Let's try one more real quick. Here we go. We've got Na2CO3. What is that? Sodium carbonate. And according to solubility rule number 1, sodium compounds are always soluble, thus it gets an AQ. And we're going to add that to LiBr. What is that? You're correct if you said lithium bromide. Also soluble because rule number 1, lithium compounds are soluble. So we have 2 soluble compounds, which means we have sodium, carbonate, lithium, and bromide ions floating around in water. Let's see what kind of reaction is this. Combustion, single replacement, acid base, or double replacement. Which one is it? You're correct if you said double replacement. We have 2 metals with 2 non-metals. So we're going to have a double switch. So who is sodium's new partner going to be? Has to be a non-metal. Metals go with non-metals. You're correct if you said Br. And then who is Li's new friend going to be? You're correct if you said carbonate. So we switch sodium with the Br, lithium with the carbonate. Notice I put the metals in front. By the way, that's important. We always put the metals in front of the non-metals. That is correct. Also, notice I did not bring this 2 over. Again, we don't copycat. Do not bring the 2 over. What do we need to do to figure out our formulas? You're correct if you said check the charges. What is the charge on Na? First column. It is a +1. What is the charge on Br? It's a halogen. Let's find it. There's Br. It's in the -1 column. Oh boy, I don't do that very often in Chem 130, but that's +1, -1. That already adds up to 0. It is neutral. It's just 1 Na and 1 Br because the charges told me so. +1 -1 equals 0. What about Li? What's the charge on that? It's in the first column. +1. What about carbonate? CO3. Well, we looked at that earlier. It's one of our polyatomics. There it is. CO3 carbonate has a -2 charge. All right, +1 -2. Oh, that does not add up to 0. What do I need to make the Li and the CO3 add up to 0? If you said another lithium, you are correct. We need 2 lithiums +2 total to go with the -2. So we need 2 lithiums for every 1 carbonate. Thus, the formula is Li2CO3. All right, so we've got our charges done. It's time to figure out our states. Let's look at our solubility rules. Lithium compounds are always soluble. So the lithium carbonate gets what? You're correct if you said an AQ. Gets an AQ. What about sodium bromide? Na, rule number 1, soluble. So that also gets an AQ. These are both AQ. What does that mean? Did anything actually happen? Well, let's think about this. I started out with a beaker of 2 Na pluses floating around with a CO3 2 minus floating around. I started out with a beaker with Li plus and Br minus floating around. And I ended up with a beaker with Na plus and Br floating around and Li plus 2 of them and a CO3 minus 2 floating around. So everything's still floating around. So did anything actually happen? No, everything is still just floating around. This is actually a no reaction. So you should be able to recognize a no reaction. When we have a double replacement reaction and both our products are aqueous, then nothing happened. They're still floating around in water. Nothing came together, bonded, and made a solid precipitate. So nothing actually happened. It's a no reaction. For fun, let's go ahead and balance it anyway. So I'm going to give you a chance to balance it. Hit pause. Okay, so we can still balance this even though it's a no reaction. There are 2 NAs, so we need a 2 in front for 2 NAs. That gives me 2 BRs, so I need a 2 in front to give me 2 BRs, which gives me 2 LIs, which I have 2 LIs floating around in the beaker. And I believe that is balanced. Let's double check. 2 NAs, 2 NAs, 1 CO3, 1 CO3, 2 LIs, 2 LIs, 2 BRs, 2 BRs. So yes, that is in fact balanced. We can put 1s in, but we don't have to. 1s are optional. But the important thing is this is actually no reaction at all. So double replacements can be no reactions if we do not make a solid precipitate. Thanks for listening. I hope you can join me on some other videos. Study hard. Good luck.